Okay, well, thank you very much. So, as it was Peter already said, I'm here to present Susana's slides. So Susana's over there. Unfortunately, she fell ill just before we were about to leave. And so she asked the organizers whether this is possible, and the organizers kindly agreed to do that. And so this is about the relationship or some aspects of classical and quantum biology. And to start with, we have here a chart where you see on the right upper corner very large objects like the brain or so, which operate on large length scales, relatively large length scales, but also slow time scales, so maybe seconds, milliseconds. And here is an area where we believe that most of this for sure can, well, let's say we feel that this can be understood from classical physics perspectives. But we equally know that when we work our way down to go to smaller to shorter timescales and smaller length scales, eventually we arrive at the level of atoms and molecules where we do know for sure that quantum mechanics rules supreme. And so therefore, we also expect that somewhere in between, there must be a transition where biological phenomena will go from the being explainable very well by classical physics to requiring quantum physics. And one of the questions about this field, of course, is where is this boundary? Is it the relatively large scales where it really makes very non-trivial effects, or is it really only that we need to understand molecules from a quantum mechanical point of view? So that's the first question that needs to be answered here. But then you can also expect that being on this border between the classical and the quantum regime, this might actually offer also some interesting opportunities, because now you can imagine that by relatively weak and small changes in the system, you may either increase the classical physics part, so the noisy part, and therefore suppress quantum physics, or you might isolate it a little bit better and then bring out more quantum properties. So here nature may also have a particular way in tuning their systems to make use of both sides. And this is in fact one of the things that will be explored in this talk. And of course, in the end, the question is, if there are some quantum phenomena at the small scales, do they have any impact on the larger scale? So do we need to understand them to really understand biology? Now, this is also interesting from another point of view. I mean, on the left upper corner, you see a machine. It's a classical machine, lots of mass, little surface. But you can also interpret proteins and small biological objects as machines. So we go and take the macroscopic machines and we go to nanoscopic machines where the surface to volume ratio grows very rapidly. So that means that there's also more opportunity for the environment to interact with the machine. There's more noise. There's not a weak coupling assumption. So certainly thermodynamics will have to be changed. And also typically these processes work much faster. And so there's also more opportunity for quantum mechanical dynamics to play a role. And this potential interplay between coherent dynamics and environmental noise will be of interest to us here. But it's also interesting that we will also, I think, maybe see some of this in the next lectures. There's also a thermodynamical aspect here, and it is not standard thermodynamics, but it turns out that the modern formulations from quantum information that reformulate or generalize quantum thermodynamics to the nanoscopic scale can start to actually tell you new ways in which you can, for example, provide bounds of how fast or how efficient photoswitches, biological photoswitches can be, which is an interesting possible also direct. Okay, so the central question is there any link between quantum dynamics and biological function? And to be frank, I mean, we don't know for sure yet. But here are a few candidate systems. So photosynthesis is a very well explored area where we do know that quantum mechanics at least is very important. there's a new concept of chiral-induced spin selectivity, whereby electrons that move through chiral structures emerge spin polarized, even at room temperature, which may have implications in biology. There's a theory of olfaction that is based on quantum processes. And there's also a magnetoreception. We do know that birds have a magnetic sense, but we do not know how they are doing it. And so I'm not going to go into terribly much detail here, but there's one observation that you can make is that certainly on the theoretical level, when you describe these phenomena, these theories that we informed, then you find that actually the first three phenomena really require the presence of a vibrational environment. So you need the electronic dynamics, and this should be coherent, and there should be quantum mechanical dynamics there, but you do need an environment in addition to make them more efficient or even work at all. And the same applies to magnetoreception, and I will explain this more in a moment, which is a phenomenon that only will work because there is a noisy environment, so something else. And so these should be examples which show a very important principle that these processes on the biological level, they may use quantum mechanics, but they will always need some form of environmental noise coming in addition. And to make this transparent in the simplest possible way, so let me briefly speak about magnetoreception. So this magnetic sense of bird, one theory by Klaus Schulten originally, suggests the following. So we have a complex, protein complex. A photon is absorbed and a radical pair is excited. And so it's two electrons, and they are initially in the singlet state. And as such, of course, they are completely oblivious to the presence of a magnetic field. So this in itself cannot be a compass at all. But now, importantly, you have, this is all sitting in a molecule, and therefore there are nuclear spins around. So you have the hyperfine interaction. So now the hyperfine interaction, when these electrons are moving apart a little bit, will break the symmetry and will induce singlet to triplet transitions. And now you're in the game, because now you have an additional dynamics that breaks this symmetry, and the strength of the symmetry breaking will depend on the orientation of the magnetic field relative to the distance between the electron and the underlying nuclear spins. And so then you have these rotations between singlet and triplet. If it's singlet, it can fall back to the original state. If it's triplet, it might generate different reaction products, and then a signaling chain might be formed that tells the bird, well, how much triplet there is on average. But here you see that this can only work if there are also the nuclear spins. There's something that breaks the symmetry. And that's the simplest example, perhaps, but in all these other examples, you can form similar explanations for why an environment is needed. And typically what you find is that if the environment is not there, the mechanism doesn't work. The environment is too strong, then also the mechanism doesn't work anymore. And here, if the hyperfine interaction would be extremely strong, then it would actually not lead, would suppress completely these oscillations between singlet and triplet, and the compass would not work. And so there's an intermediate regime where this is optimal. And interestingly enough, it seems that this optimal regime is where the interactions between system components are roughly as strong as the interaction of each component with its environment, very broadly speaking. And that's a very awkward regime, actually, because master equations do not apply. The ones that we use in quantum optics simply don't apply because they make the weak coupling assumption, for example. Rate equations are also wrong because quantum mechanics is still there somehow. So we certainly also need already new methods to actually describe this dynamics accurately. And because we also start to learn that really the final structure of these environments is relevant. And so therefore we really need new simulation methods to describe this dynamics. And so what you would like there is that is a method that is, of course, numerically tractable. You have a very large system. You have system and environment, many components. And so it should ideally scale somehow well in the size of the environment. You need some handle to increase the precision systematically, so that you can say, I needed more precision, so I increase whatever the bond dimension of my matrix Borel states or something else. And ideally, you would also like to have some way of bounding the error that you're committing in these simulations, so that in the end you get an answer plus an interval that tells you, okay, somewhere in this interval around the answer is the true value. No. And without going into detail, over the last 20 years, perhaps, there's a whole zoo of methods that have been developed, and it's still going on. They are, to a large extent, initially many of them have been formulated independently, but most of them can somehow be cast in the language of tensor networks that we are used to in quantum information, actually. But that also shows you that they will be limited in some way, because tensor networks fail when there's too much entanglement. So if there's too much entanglement between system environment or between the environment degrees of freedom, then these methods will start to become computationally challenging at the very least. And therefore, it is also of interest to start to think of maybe building quantum simulators, either digital or analog, that might actually simulate some of these phenomena. Because actually, as I will show you in a moment, we start to realize that even relatively simple experimental data that we are taking are very difficult to analyze with these classical methods, and therefore also it's difficult to find out parameters that are underlying these systems. And so one specifically very, very complex setting is the setting where you have spin degrees of freedom or electronic degrees of freedom and vibrational environments. So that's very unfriendly for simulations. And so therefore, you might think that, for example, a trapped ion setting might be very attractive here, where you have your spins given by your ions, and they happily live together with their vibrational degrees of freedom. And I mean, we have learned, the experimentalists have learned over the last 20, 30 years, how to couple these spins to the vibrational degrees of freedom. So therefore, we can now build up in principle systems that are really electron vibrational dynamics emulating simulators. So that would be very interesting. There are first some baby steps that have been taken towards in this direction, but I think a lot more needs to be done. And in fact, there are some experiments that have been carried out, but those have missed out a very crucial aspect. They just took ions in that, or superconductors, and then they just put a classical noise source. And that is not what biological systems are about. There it is, you have your electronic degree of freedom, it will interact with the vibrations, it will set the vibrations in motion, but also the vibrations will act back onto your electronic degrees of freedom. And this exchange actually makes it non-trivial and also difficult to analyze. So really one still has to go a step further to really build simulations that can capture this aspect. And what is it that we would like to actually compute with these methods? And so when you, for example, go to photosynthetic systems, then there the timescales are very fast, so you do ultra-fast laser spectroscopy. And so you either do pump probe or absorption spectra, or you do what is called 2D spectra, which is very similar to what you do in NMR. You kick the system a few times with short laser pulses, you change the separation between those kicks, and then you measure the response of the system. And so you have to do this over extended time scales, and you have to model this interaction between the light and the electrons, and then the electrons and the vibration quite accurately. And you have to really obtain a lot of data. And we can do this now for 2 electronic sites and their environments, but for maybe a larger biological complex with 6, 7 sites already, this becomes extremely challenging numerically if you want to do this accurately. And this is not a very large system at all, so it could well be conceivable to do this in a trapped ion setting. So, but why? Now you can say, well, okay, but maybe we can do this with relatively approximate methods and we get everything that we want to know. But that is not quite the case, as I will want to convince you now. And so what do we want to learn from these methods? Well, we shine in the lasers, we measure the response, and then we want to learn what are the electronic coupling strengths, what are the coupling strengths between the electrons and the vibrational degrees of freedom, and all these parameters we want to back out because we're really difficult to compute them, so we need to measure them in experiment. And so therefore, we take these 2D spectra and we infer something else. And so that we can only do if we can make simulations of the dynamics given some assumed parameters, and we try and reproduce the spectral data that we are measuring. And unfortunately, or fortunately, depending how you see it, these vibrational environments are very, very complex. So they have vibrations that go from very small, moderately small frequencies of few wave numbers up to maybe 2,000 wave numbers. And there are many, many vibrational degrees of freedom there. Some are short-lived and they give a broad background, but some are very short-lived and have a very long memory time, and therefore give rise to strong non-Markovian dynamics in the system. And we certainly now start to realize that we really have to take into account all of these modes, the entire range, very accurately, to learn the correct values for the electronic coupling strength in these systems. And this only has become possible recently because of these new simulation methods. And what you can do is, maybe I should go, then you see on the left here, there's a very, very simple, in the left panel, outermost left panel, there's a very simple approximation to the true spectral density of this vibrational environment. It's made very smooth so that we can actually treat this relatively simply with numerical methods. And then you can use this to approximate an absorption spectrum, for example. And it looks pretty good. Everybody seems to be happy with that. And then you infer from that, you choose the electronic parameters, you choose them right, 70 wave numbers in this case, and you get a reasonably good approximation to the spectral density, to the absorption spectrum. But then if you take this electronic coupling strength and you do the true simulation, you take into account the full vibrational environment with all its peaks and across the entire frequency range, then you see that actually you're starting to miss features of this absorption spectrum. So something is obviously wrong here. So these frequencies that we have in these vibrational modes do play an important role, even if they're quite far detuned. And then what you do is, well, you do a new fit. So now with these numerically exact methods, you get a new parameter for the electronic coupling strength, and it turns out you have to double it to actually get now a really good fit to the data. And so that shows you that it's really important to be able to simulate really very complex system environment dynamics to back out parameters correctly. And this can make a difference of a factor of 2 or possibly even more in some settings. And that, of course, has significant consequences about our understanding of these systems because doubling the electronic coupling strength makes a huge difference in terms of what correlations in the electronic degrees of freedom might emerge in the system. And so this is really a great challenge that we're also facing in this area, that the systems are very complex. We cannot clean them up quite as much as we can do with quantum optical systems, because then they lose their biological relevance. And we have to make these experiments in complex systems with disorder, and then have to learn about their properties from those experiments. And that's perhaps also one of the reasons why the development or the progress in this field is relatively slow, because of the experimental challenges that are involved in that. Okay, and so with that, I would like to close and thank the team. This is, of course, a collaboration effort, and also the funders. Thank you.